Start. Hello and welcome back to Calculus 3. This is section 13.2, part 2. Again, so double integrals over general regions. Last time we said that general regions would be any type of the domain region in xy plane, which was different than what we had with the rectangular regions. Rectangular regions had all constants in the limits of integration, and now our general region, which is what we did last time, had the functions. And we said that we are going to look at either dx or dy to decide which way we are going to set up the integral. We said that in some cases, certain combinations are not possible. In some cases, both combinations are possible. And in some cases where the both combinations are possible, one combination is far easier to deal with than the other. So we are supposed to take a look at all of the combinations of flavors, right? And what we did last time is a few basic examples where we outlined that now our region depends on those functions that will bound the region over which we have the shape that builds up. And we see that the outer integral has constants, the inner integral has those functions that bound the shape, right? And we talked about it as a stencil, right? It's a cookie cutter stencil that presses onto it, so the outline of that stencil is given by the functions and these bounds. Now, the most important skill which everyone must master is the one that relates the limits with the picture, right? The graph of the domain. So once you are given the domain, you must be able to, so the region, right? The domain, xy, you must be able to come up with these limits, or if the integral is given to you and we need to switch the order of integration, right? Hopefully not, we have to be able to draw the domain from those limits, and then, so that's the goal for today. We already went through all of the vanilla problems last time. We know how to calculate, and in green over here, I said understanding the region R. So the problem was just given in a textbook, problem 20. They did not talk about it, they just said compute. And you know how to compute double integral. You compute the inner one and then the outer one. So that was not an issue. What we really need to do is to understand the green stuff over here, which is the way to transform, as I said, the limits into the picture. And then to see if you can revert it back to have the other. So we'll take a look at those problems. This was another example where we decided whether we're going to use dx dy or dy dx. And another example with the same decision. Now let's take a look at a few more examples that will further look into these things. So let's start with problem 31, which gives us a graph two functions, y equals 2x and y equals 3x minus 9. Our region Let's use light green. So our region is here. This is region R. And we are supposed to write the integral. Now, can anyone tell me from the last class what was the difference between having a double integral with integrand being 1 or integrand being some kind of function? What's the difference? Yes?
If there's a function that's like the top, like the shape of the top of it.
Okay.
If there's no function, it's just flat on the top, right?
That was not it, but we have to distinguish between those two.
If you just have one, that's the area of it.
Yes.
But if you have an f of x, y, then you have the volume.
Yes. So, if we have the double integral with the function in here, dA, that is computing the volume, because this is area times the height, f of x, y, z. So you have dx times dy times z. That gives us 3D. So it's volume that we are computing. If we only have double integral dA, which means the integrand is 1, in that case, we are only calculating area because z is not there, right? So we can use double integrals to compute area if there is no function in there, or we can use double integrals with function in there to compute the volume of the shape. Now, the z function, the f of x, y, right, will tell us which way the function curves on the top, right, what it looks like in terms of our functions. Now, problem 31 is not giving us any functions. They just give us a region and say compute the integral. Therefore, they want the region. They want the area of the green region, right? So we are going to set up our integral. Now, these are the, again, skills from last class. Do I use dy dx or dx dy? So that's our, so dx dy or dy dx. So that is the question that we have to address. Remember our friend? Dx representative rectangle. Oh, I already see you know which one we have to use. And you're using the same. Great. So we have to use, as the main one, the outer integral, dy. Very good. Now, let's say you can't spot that right away. Let's draw the wrong one. Let's draw dx. If you draw dx, observe that the top of the, so if you draw dx, you are aiming for dy dx, right? If you draw dx rectangle, representative rectangle. So now, observe, your goal is to draw a rectangle, whether it's dx or dy, which will always have the same function on its edge. Well, the top of this dx is always on 2x, that's good, but the bottom is not always on 3x minus 9. If I am to draw another dx right here, you see that the top is still writing 2x, the bottom of that rectangle is on 0, which is a different function than this one. If you have this situation, that means that you have to have two integrals. There will be one integral for dx to swipe up to here, and then the function on the bottom changes, so you have to have another integral for the second part, for the second dx. And that's the problem. So since that didn't make us happy, let's try dy. You try things. If it works, great. So now we have dy. Observe dy. Left-hand side of dy is always on this function, and the right hand of dy is always on this function. That works. Which means this is the one that we need to pick in our setup, because the dy rectangle is always following the same function on each side. So now to set this up, we will have double integral. We are going to use 1 as the integrand because we are looking for this area, and we have dx dy. The next order of business is to put the limits. Outer integral is y, and those have to be constants. So what are the two constants that bound our y, looking at the picture? 0 and 18. Very good. So the lowest this dy can be is at 0 level, and the highest it can be is at level 18. So 0 to 18 for the outer integral. And how about for the inner? What is the dx situation? Well, these need to be functions of y. Right minus left. We have to solve these. If you are taking, always remember, always go back, when you're setting these integrals up, always go back to integral in Calculus 1. What was the first thing you ever seen? The first integral you ever seen was this integral, where we go x, 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 right? Limits are x, function in terms of x, dx. That's the first integral you ever seen. So this limit here has to be some kind of a function x1 equal to stuff, and the limit up there has to be, again, some x2 equal to something, because again it has to be x, 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 as much as this was y, y, y for the outer. They all have to match. So now I know that I need these two functions. I don't have them in terms of x. So what should we do? What should we do? Yes. So we are going to solve these. We have y equals 2x. We are going to solve it for x, which Andrea said it's x equals y over 2. So it's y over 2. We are going to plug that one where? Lower limit, upper limit? Lower limit, good. It's right minus left. Okay, right minus left. So that one was the left one, left side of the dy. There goes on the bottom. And then we have the other one, which is y equals 3x minus 9, which flips into y plus 9 over 3. Y plus 9 over 3. Great. So is everyone good with us? We all understand where these things came from? Good. All I need to do now is to compute this. So we do the inner integral first. So 0 to 18 gets copied. The integral of the inside is x, computed from y over 2 to y plus 9 over 3. And then we have dy. This is our first checkpoint, because you see that these guys are going to plug in for x, and then the next integral will be all in terms of y, and you're integrating in terms of y. So that's good. I mean, you will know when you mess up, because nothing will make sense, right? You will be done with the integral, and you will have a function in terms of, I don't know, something that makes sense. So you will know if it's wrong. So what do we get? We get our integral 0 to 18, top limit. So that's y plus 9 over 3. So let's go with y over 3 plus 3 minus y over 2. Don't forget these parentheses. You know I'm allergic to that. And then we have y over 3 minus y over, so this is 3 minus y over 6. Integral 0 to 18 dy. It's time to integrate. We have 3y minus y squared over 12, because y squared over 2, 2 times 6 is 12, computed from 0 to 18. We do not have to worry about 0, because it's a polynomial. But if we have cosines and or exponential functions, we do have to worry about it. So we have, what do we have? 3 times 18 minus 1 over 12 times 18 times 18, which is 9 times 2 times 9 times 2. There we go. And we have these 12 cancel with 2 and 2. And you get a 3 over here, which cancels with the 9. You get another 3. So 3 times 18. Oh, actually, no, you can factor out 3. So that's going to be 18 minus 9, which is 9. So 27. Good enough. So that will be, or you can use the calculator. You know that. Well, so this problem, we have seen that, yeah, this is the first problem that we had to do dx dy. All previous problems were dy dx. The choice was made because on dx dy because lazy, right? The least energy state. We didn't want to do 2 integrals. Can I do 2 integrals? And the answer is hell yes. Yeah. Should we? Obviously no. But let's at least set it up. So we're all happy with that. And then, you know, those of you who like pain, obviously you go home and compute this, making sure you get 27. Otherwise, we can retire mathematics. You have to get the same answer, right? So way 2 on the same problem is going to be setting it up. I'm just going to draw the shape and say this is 2x, y equals 2x. This was y equals something, 3x minus 9. And this over here was 9, 18. And this was a 0. I need this value here. So that's when the y is equal to 0. So that better be 3. So now if I want to use dx, well, that dx will cut the region into 2 regions, region 1 and region 2, because the function on the dx, on the bottom of dx representative rectangle swaps from y equals 0 to y equals 3x minus 9. And that's the reason why we have to have 2 double integrals here. So the first double integral for region 1 would be the double integral dy dx, right? Plus the second integral, also dy dx. This is for region 1, and this is for region 2. The integral for region 1 will swipe from 0 to 3 on x, so 0 to 3. And on the region 2, will swipe from 3 to 9, right, as a dx. So now we see that we cover the entire region from 0 to 9, right? But it's done in 2 installments. Now, why do we have 2 integrals? Well, the first delta x, which I'm going to represent by this black rectangle here, so that's delta x, and then second delta x here, also delta x. So the first one, as you can see, the bottom rides y equals 0. So that's the 0 over here. And then the top rides 2x. On the second integral, the bottom rides 3x minus 9. And the top is 2x. And this is the reason why you must have two integrals. Now, you all know how good with computation I am, and fast, and all of that stuff. So it's 27. I mean, that's obvious when you look at the integrals. It's 27, so there you go. So in this particular problem, you see that both dx and dy are possible. However, one is less work than the other. So that's that part. But then we have examples where one of the two possibilities is not possible at all. And that is when the function curves in a way that dy or dx cannot be. Think about the parabola. For just for a second, think about the parabola. If you have a parabola like this, can you write dy in it? And the answer is no. You cannot have dy inside the x squared parabola. Patience, young Padawan. This goes to space and comes back. The issue over here would be, obviously, when the right and the left, right? When you do the integral, right, it will be the same function on both ends. And you will not be able to compute stuff, right? So when you have this situation, it can be sideways as well, and you try to set up dx. It doesn't work, right? So you are forced to use the other one. And if the other one is requiring two integrals, well, right, I have a square jar for that. But there's nothing you can do. Nothing you can do. So you have to be mindful of those. If we run into a problem like this, I will point it out. Let's take a look at the situation where you have to change order of integration. I just need to hunt down a problem for that. Changing order of integration. So let's work on two of these examples, and that would be the section. First example, we'll take something simple so we can understand what's happening. So reverse the order of integration. Problem 58 has 0 to 3 on the first integral, 0 to 6 minus 2x on the second integral. They give you just f of x, y, and they have dy dx. So they want this integral switched into double integral of f of x, y, dx dy. Now, this is just an exercise. Has nothing to do with anything other than the mechanics of switching it. Why we need to do these things? Stay tuned for the next example, okay? So right now, we're just going to do mechanics. Now, this is going to be the green stuff that I did last class. Understanding the region that it's given to you, looking at the limits. So, I know that our domain, our region, is going to be the floor, xy plane, on which we walk. So I'm going to draw, hopefully, there we go. I'm going to draw the xy plane. Now, at this xy plane, I have to, oh, that's a 6, right? Nice. All right, if it's a 6, then we'll need space. We need to draw this. Go immediately for functions. This function is paired with the inner d, in this case dy, so this is y equals 6 minus 2x. That is y equals negative 2 over 1x plus 6, right? If you are still looking for this, the formula, y equal mx plus b, the one that you learned in algebra. Now you graph this. We have our y-intercept at 6, so 1, 2, 3, 4, 5, 6. The slope is 2 down, 1 over. So 2 down, 1 over. It's going to hit 3. And then you connect those. It's like the connect the dots and then color, except you don't have, no, we do have to color actually. So it is just like that. Now we color, because that's our region. Now if you have multiple lines, you have to worry about other things, other bounds. Now let's see if it matches everything. This function over here, y equals 6 minus 2x. That's the bound for our dx from the top. The bound for our dx from the bottom is y equals 0, which is x-axis. Oh, perfect, right? Now I need the left and right bounds for dy. Well, what are the left and right bounds? Well, from 0 to 3. Great. This line is x equals 0, which is the y-axis, and it stops at 3. So it works, right? You see that the y is stuck, dy is stuck between 0 and 3, and x is stuck between 0 and the function. Great. So now we are going to look at the picture. So we are done with this. We don't need this anymore. That's done. We use it only to come up with a region. Then we use the picture that we have, right, for our region R, to come up with our integral. In this case, we need it to be dx dy. Well, I need dy. dy is the main rectangle, so I am going to draw horizontal dy representative rectangle. Apparently. Maybe eventually. So now, when I draw this representative rectangle, which will eventually appear, there it is. It's called delayed reaction. We have to work on those bounds. So it goes from 0 to 6. Do we all see that? The lowest it can be is 0. That's the outer limit, 0. And then the highest it can be is 6. That's for dy. You worry about lowest and highest. For dx, you worry from left to right. So now we have 0 to 6 on outer for dy. Now we need the inner ones, right? Clearly, it goes from 0 because the left-hand side, which is the lower limit, is always writing x equals 0. And the right side, we have to flip this one. We know that already. So, what do we have? We have 2x is equal to 6 minus y. X is equal to 6 minus y over 2. Perfect. So that's 3 minus y over 2. Ta-da! And if you are going, why? Let's see why. Another example from the textbook, problem 64, is 0 to pi, x to pi, sine of y squared dy dx. What is the first integral that you have to do in this case? Which integral? In respect to y. Good. Why? No, I mean question. Why? Why do you have to do y integral? For here. If I had y, use basic U sub, we're done. Not a problem. We don't have that y. We cannot integrate this. Actually, we can integrate. How would you integrate this?
Change the sign. I changed the integrals and the order.
Well, yeah, no, that's in Calc. Yeah, that's in Calc 3. We are going to change the order exactly, and we will be able to do it. But how would you integrate if you just had integral sine x squared dx? There was nothing else on the page. This is it. How do you do it? Is that Ryan playing the music over there? Oh. Oh, come on. Update. Let me... Generally, I don't have issues with Calc, but apparently today we did. By the time this disconnects and reconnects, oh! So this is equal to sine x, then you take this x and make it a square to this power, and then just write some polynomial out, and there you go, the best, yeah. You can integrate anything with that thing, right? All right, I'm waiting for this thing to restart. Try, no, that one, this one. So try to draw the region by the time this restarts. I need to restart the projector because it got stuck. It's still streaming, so at least that's good. I think it would be an issue with how many nodes internet connections are available. So now
I guess they're all having 247. The middle of it just goes down and starts.
Yeah. So try to draw the region, looking at limits. This is something that you must know, and we are going to up this later with the 3D. Yeah.
Video is as soon as I stop streaming, shut off the OBS, it immediately cuts off the video and then post it automatically. No, I don't touch anything.
It's already enabled?
Yeah, because I put that file before. Beforehand. And as soon as it comes off, it uploads with the comments on
Share your own channel.
Yeah. And then all I need to do is to go my notebook, my OneNote, and I export the virtual note as a PDF. Upload that. So that's the work. But it's good for you. And that's it. So my But you can count number of x minus 1, subtract 29. Even though the level cannot get. Well, I guess.
Right. We said no coughing? It found the projector, it just doesn't want to connect again. So, well, this is the last example. I'm going to, I guess, chisel this one on the board, and then we'll restart everything for the next section. Hopefully, it kicks in. Did you? So try to draw the region and come up with the integral. All right, so let's please stare at the problem for the time being. So we're talking about problem 64. Let me see if I have these chisels work. It's invisible ink. Problem 64. Double integral 0 to pi x to pi sine y squared dy dx. See, I know how to write. See that? If you ever wondered, some students been with me for 2 years now, they haven't seen this. All right, so I'm going to draw the region. I said draw functions. Which functions do you have? You have a function y equals pi and y equals x. So y equals x, y equals pi. And you need to go from 0 to pi. Question. So this is where pi is. So you have this nice little square with the diagonal. Where's the region? Top or bottom? Top. This is the region right here. Why is that a region? we have 0 to pi on x. I do have 0 to pi on x. But then this one is x to pi. So this is x, and this is pi. What's the bottom one? 0 to x, exactly. So this region over here is 0 to x, and this region over here is x to pi. It's a subtle difference for the inner integral. This is the thing that really kills the problem if you get the wrong reading this, right? Now, once you have this done, right? So we have the region on the top in between y equal x and y equal pi. So the region is on top. And in the notes, I shaded that region pink. That's our region. And now we set up the other double integral, which we can solve. So what do? I have the same sine y squared, and now it's going to be dx dy. So dy, outer limits, so y, the lowest y can be is at 0. The highest it can go for dy is pi. And now the right-hand side is going to be x, and the left-hand side is, x on the top, 0 to x. So as we switch the integral, this is what we get. Now compute this integral. No pressure. You have 18 seconds. Go. Come on. Yeah. You can bring backup.
Oh, no.
Yeah, you know who backup exactly, and he has to go. If you come up, he has to go. See? So I'm just going to solve this real quick and shut off the stream so I can restart everything. Oh, this is supposed to be y, not x.
Oh.
No one said anything. This has to be x1 equal, x2 equal, right? Because it's x, x, x. So it's x equals to y when you flip the function. I'm sorry?
Why is it y to pi?
The lowest y can be is the representative rectangle at 0 level. So it's constant on the outer integral. 0 to highest is pi.
Okay.
Right, so imagine it sliding up. Right, it starts at the bottom and it goes up, covering every single point along the way to give infinitely thin rectangle to get the area. All right. Bye to these guys.